Okay, so welcome to this fourth lecture on the electrochemistry topic. I'm Dr. Devendra Kumar. So today we'll be talking about concentration cell. So how are these concentration cells different from the galvanic cells? So they are similar to galvanic cell in the sense that they also produce electrical energy, but at the same time they are also different from the galvanic cells because their mechanism of action is little bit different. So in galvanic cell, electrical energy is produced from the chemical reaction taking place. So spontaneous chemical reaction takes place there and electrical energy is produced. So that particular cell is galvanic cell. However, in concentration cells, EMF, the electromotive force or the electrical energy, is not produced due to the chemical reaction, but it is due to transfer of matter from one half of the cell to the other half of the cell because of their difference in the concentration. Okay, so that is why these concentration cells are of couple of different types, which we will discuss now. So over here again, the EMF arises due to the transfer of matter, not due to any chemical reaction. So simply the matter, the chemicals, they are transferred from the one concentrated part to the dilute part. This is what happens till their concentration become equal. All right. So concentration cells are of two types. So broadly, they can be divided into two parts. First category is electrode concentration cells, where there is a change in concentration of the electrode. All right. And the second one is electrolyte concentration cells, where what happens is your electrolyte, your solution of the electrolyte, that differ in the concentration for the two half cells involved. So electrode concentration cells, so just to define, in these cells, two like electrodes are dipped in the different concentration. So their electrode concentrations are different. Uh, they are dipped in the same solution. However, the electrolyte is same, but it is the concentration of the electrode. So we will discuss in detail in next couple of slides how this uh, concentration cell, electrode concentration cell works. So for example, once you have two hydrogen electrode, which will act as cathode and anode respectively, but the partial pressure of the hydrogen gas is different there, right? And but they are dipped in the same solution of H ions, for example, maybe HCl. So such type of cell is known as electrode concentration cell. Okay, so electrode concentration cells. So here is an example. Here hydrogen is at a pressure of P1 in contact with the platinum electrode, and hydrogen is at a pressure of P2 here in contact with platinum electrode. Both of these electrodes are dipped in the same solution of the electrolyte HCl because this electrolyte is common, so you can use the same solution. Now, how the right hand side, our here cathodic reaction will take place. So from the HCl, reduction will happen and H2 will be produced at a pressure of P2. So you can simply write 2H ion plus 2 electron going to H2 at a pressure of P2. And at the left hand side, again anode, it will work as an anode. So oxidation will take place. So H2 oxidation of hydrogen. So H2, which is present at a pressure of partial pressure of P1, that will be oxidized to give two H ions in the solution and two electrons, right? So overall reaction, if you write, you just add these up, these H ions and electrons cancel out. So hydrogen at a pressure P1 goes to hydrogen at a pressure of P2. So this is what we have here. So simply you can also write the EMF of the cell, E cell, we can derive that too. So here we can see the overall reaction is independent of concentration of electrolyte. H ion concentration is not involved. Only partial pressure of the electrode hydrogen gas is involved, right? So at moderate pressures, you can consider them as the ideal gas, and the ratio of activity is ratio of the partial pressure. So if you apply Nernst equation right here, so it will be E equal to E naught minus RT by NF, N is 2 here, RT by F is 0.0591, log of product by reactant. So hydrogen at a pressure of P2 divided by hydrogen at a pressure of P1. So that will be your equation for the EMF. And by definition, we know that E naught for SHE is 0. So this will be 0. Ultimately, this is divided by 2. Ultimately, it will be 0.02955 log of P2 by P1. And if you take this negative sign inside the logarithm, it will become P1 by P2. So this EMF of the cell is positive only if P1 is greater than P2, right? So this means this cell will produce electrical signal, electrical energy, as long as this pressure P1 is greater than P2, and it will continue to produce that electrical signal till their pressure become equal. So this is nothing but is equivalent to the spontaneous expansion of hydrogen gas, where it is at a higher pressure and it goes to a lower pressure side. So the second example is, second example is similarly we can take a mercury electrode example, amalgamated mercury electrode, which is amalgam forming an amalgam with lead, right? So here lead's concentration is C1, here lead concentration is C2, the common electrolyte is lead sulfate. At the right hand side, you can write the cathodic reaction. So in this amalgam, lead 2 plus will go, right? So reduction will occur. So lead 2 plus will be reduced to form lead with a concentration of C2. And in the left side, oxidation will occur. So this lead at a C1 will go to lead 2 plus in the solution. And ultimately you can add these up. Ultimately this will be C1 by C2. EMF of the cell is cathode minus anode. So cathode minus anode, this lead concentration cancels out. So ultimately it comes down to C1 by C2, right? And 2 electrons are involved. So again, this EM of the cell will be positive as long as C1 is greater than C2, right? So this means ultimately what happens is there is a transfer of lead's concentration from higher concentrated solution electrode from C1 to C2, which is lower in concentration, right? And it will continue to produce electrical energy till both the concentration of the electrodes are equal. So similar, we can try a numerical problem here. So here you are given a electrode concentration cell with the difference in the partial pressure of the hydrogen, which are 600 and 400. And of course, you know that P1 should be greater. So it is greater here. So all you need to know is just apply this Nernst equation here. E cell is equal to 0.0591 by number of electrons log of P1 by P2. P1 should be greater in order for this cell to work. So P1 is 600, P2 is 400. Units are same, so they cancel out. So you just calculate this log part. Ultimately, you should be able to get this answer: 5.19 into 10 raised to power minus 3 volts. Right. So you can try more numerical problems according to this. So second part is electrolyte concentration cell. So electrolyte concentration cell, as just the name suggests, here there is a change in concentration of electrolyte. So these type of concentration cell involve where you have the electrolyte concentration, they differ in the electrolyte concentration. For example, shown here is the example or notation, cell notation of the electrolyte concentration cell, where copper 2 plus electrolyte concentration is 1 molar in the cathodic compartment, and in the anodic compartment it is 10 raised to power minus 3 molar. So we need to derive the cells EMF for these. And how do they? So a pictorial presentation will look like this. Here the same cell is on the left hand side figure. The same cell is shown, the copper 2 electrode, they are uh, connected via salt bridge. Dipped copper rods are dipped in the zero point 0.1 molar solution of copper. Here it is 1 molar, and initially it is giving out a signal of 0.0296 volts. And ultimately what will happen, so dilution will take place from higher to lower. So here reduction will occur, here oxidation. So reducted part, more of the copper will deposit here. So in the right hand side figure, you see that copper is being deposited with time, and this will act as an anode. So copper is lost from here, and this reaction will continue to take place till both of these concentration of the copper ions are equal. So which is 0.55 molar in copper 2 plus, and at that time the signal will be 0.00, because right now it is now totally reversible cell. All right, so you can write oxidation reaction occurring in the left side will be copper going to copper 2 plus 0.1 molar concentration, 2 electron oxidation. Here 2 electron reduction of the copper 2 plus with 1 molar in concentration right here, and will give you copper solid. You add those up, overall cell reaction will be copper going to copper 2 plus, copper 2 plus going from a higher concentrated solution to a lower concentrated one, right? So this difference, so all you can see is there is no redox reaction taking place here overall. It is just the matter is being transferred, the copper ions are being transferred from the right hand side electrode to the left hand side, to the left side. And this is till these concentrations become equal, which is in this case is 0.55 molar. Okay, so electrolyte concentration cells are further of two types, right? So you can have the cells without transference of the electrolyte. So this means two electrolytic solutions are not in direct contact with each other here, and transference of ion doesn't take place. So this kind of cell uses a salt bridge, which provides a mechanism but doesn't involve direct involvement or the transfer of ions there. Second one is concentration cell with transference. So here the two solutions are directly in contact with each other through a porous membrane or so, right? So and hence transference of the ions take place here. So we will focus on the electrolyte concentration cell without transference. So without transference means they are linked by a they are connected via a salt bridge here. So here one metal electrode is there with M ion concentration. Let's say it is zinc rod dipped in zinc solution, zinc sulfate solution with a concentration of C1. Here concentration is C2, but it is the same metal, zinc electrode, right? Here you have potassium nitrate, potassium or potassium chloride in this uh, salt bridge with the agar agar. So now in these, so I just took this example of zinc. So you have in the right side you have zinc sulfate solution with the activity or concentration of A2 or C2, and left hand side you have in the anode compartment activity is C1, right? So they are differing in the electrolytes concentration, all right? And this double vertical lines, they denote that they are connected via salt bridge, which means there is no direct transfer of the ions, so it is without transference. Okay, so now ultimately what will happen, so on the right side we will write the cathodic reaction, so that will be the cathodic reaction taking place on the right side. So zinc ion with the activity of A2 will be reduced to form zinc solid. Then left hand side oxidation will take place of the zinc, and but these activities are different, so make sure you note that down. And then overall reaction will be simply zinc ion A2 going to A1. And similarly you can define find out that EMF of the cell, what it will be, it will come out to C1 by C2, right? And C1 should be greater than C2 here for that to be positive. Okay, so electrolyte concentration cell with transference. Second type is with electrolyte concentration cell with transference. So with transference means the two solutions are in direct contact with each other, right? So for example, this one, silver dipped in a solution of silver nitrate with 0.1 molar. Here it is 1 molar, but it is the same silver. And here they are connected, they are directly in contact with each other via a porous disc or porous membrane, right? So even ion migration can take place very easily here. So such of example of this cell is hydrogen, two hydrogen electrodes dipped in aqueous solution of the HCl with concentration A1 and A2 here, right? And the right hand side you will have reduction of hydrogen, reduction of HCl to give hydrogen. So you can write something like that: H ion with the activity A2 goes to hydrogen gas pressure, hydrogen gas is produced. In the left hand side, reduction of the HCl will with activity A1, in the left hand side oxidation occurs and hydrogen is oxidized to give H ion with the activity of A1. right? And one electron oxidation take place, and both of these differ in the H ion concentration. So you guys can simply add this together, and what you will see basically, it will, the transfer of matter takes place of the HCl from C1 to C2 or A1 to A2, which one is higher, right? Till their concentration become equal, it will continue to produce electrical signal. So once this kind of cell operates, which is with transference, so H ions are generated at the left hand electrode and consumed at the right hand electrode. And both H ion and Cl, since they are of opposite polarity, they move in the opposite direction, right? And in this cell, your ions are in direct contact, hence they are free to move. That is why at the junction of these two half cell half cells, a liquid junction potential is developed due to migration of ions. So we will discuss that. What exactly is this liquid junction potential? So let's try to understand here. Once these HCl solutions are separated, zero point 0.1 molar, the more concentrated one, and this is less concentrated HCl solution. Once they are in direct contact through this porous membrane, so this porous membrane allows the ions to move through it, right? And we have also discussed which of these HCl ions out of this H ion and Cl has higher mobility. It is the H plus ions. So now HCl will move towards this dilute solution overall, both H ion and Cl negative ion, but mobility of H ion is larger. So in a given time, more of the H ions will move to the right side, and that will make this dilute solution a positively charged near the boundary of this porous membrane, and the higher concentrated part will bear a equally negative charge due to excess of chloride ion present, and because another excess is on of H ions is here, it will carry a positive charge. So because of this migration of ions through this porous membrane, what you have is, once these two solutions are in direct contact, which differ in concentration, ions tends to diffuse from concentrated solution to the dilute solution as shown here. And ultimately what happens is, one of the ions has a higher ionic mobility, and hence that that carries some charge to the dilute part. Hence, this becomes positively charged here and negatively charged here in the um, higher concentration side of the HCl. So this rate of diffusion is proportional to the speed of ion in the electric field, which is basically the mobility, right? So here H ions move with the greater speed. So this means negative charge will be left behind here. The chloride ions, excess chloride will be left behind here. So this side of the electrolyte will bear negative charge at the contact, right? And this side, right hand side, will bear the positive charge, and this dilute solution is positively charged here, right? So now, because of this, a double electrical double layer is set up at the electrode, at the junction. Now if you can also figure out, if the anion moves with more velocity, the dilute side will get a negative charge and concentrated side will get a positive charge, right? So electrical double layer is set up at the junction of these two potentials, right? And which contributes to which basically contributes to this overall EMF of the cell. Sorry. And this potential developed at the junction of two solutions is known as, which differ in the concentration, is known as liquid junction potential, LJP, and is measured in millivolts or volts. Usually it is of the order of millivolts, like 5-10 millivolts or so. So how does it originate? Basically, if two liquid moving with the ions are there, they are have the same speed, then there will be no liquid junction potential, because none of the side will carry a charge or bear a charge. If there is a difference in velocity, there will be electrical double layer set up. The charge layer will be set up at the boundary of these two solutions, and hence there will be liquid junction potential. And magnitude of liquid junction potential depends upon the relative speeds of ions. More the difference in the ions mobility, more will be the magnitude of LJP. And ideally, we want this LJP should be minimized. Ideally, it should be zero. So how to eliminate this liquid junction potential? We can use a salt bridge, and in the salt bridge, we can have an electrolyte which is highly concentrated, usually 4 molar, 5 molar we take of KCl, KNO3. And not only that, there is one more restriction that ions which form this of this electrolyte in the salt bridge, they should have almost very similar ionic mobility or similar transport number. Or in other words, the difference in transport number of this electrolyte used in the salt bridge should be zero. So what is the disadvantage of this liquid junction potential? It affects the accuracy of our potentiometric measurements. All right. So we have already covered a couple of reference electrodes which are used in the potentiometric measurements. For example, saturated calomel electrode we have discussed, right? And silver chloride or standard hydrogen electrode is there. So what are these reference electrodes? So electrodes which have a constant potential under certain conditions, and we can use their potential to measure the potential of other electrodes, and those are called reference electrode, and their potential is basically known. So for any electrode to work as a reference electrode, there are certain conditions to be satisfied. So those different conditions are, there are four different conditions. So it should have a well defined and reproducible potential. So its potential should be same each time you carry out a measurement. It shouldn't be like it gives a different measurement or gives a different reading of the potential every time you do the experiment, right? And secondly, if there is a temperature change, EMF of this cell should not change. This half cell electrode, reference electrode, should not change, right? So this means temperature coefficient of the EMF should be almost zero. Sorry. And third condition is it is working in the equilibrium, right? So it, while measuring the potential of the cell, it draws no current from the cell. And also at this electrode, both the oxidation and the reduction reaction are favorable equally, and it is easy to fabricate. So these 4 or 5 conditions are there which are necessary so that any electrode can work as a reference electrode. Example, one of the best one is standard hydrogen electrode, which is used to calibrate that electrochemical series. But due to hydrogen involved, which is explosive, we right nowadays we don't use it. We use saturated calomel electrode or silver chloride as a reference electrode, right? So saturated calomel electrode is nothing but your mercury and Hg2Cl2 and KCl solution is taken, and we have already discussed in previous slides how the EMF for this calomel electrode is dependent upon chloride. So it is also an electrode of second kind. Ultimately, this is the reaction that takes place here as the reduction reaction at the calomel electrode. So mercurous gains 2 electrons to give mercury and the chloride ions, right? Okay, so that's it for the electrochemistry. And now I would like to draw your attention to one of the slides here, where you can solve a couple of problems based upon the electrochemical cell, EMF of the cell. So you can, there are 3 problems here shown here, so you can try those, right? And find out the concentration in the first one of cadmium, then this potential of the cell in the second one, also potential of the cell in the third one. So here are a couple of the references that I have used to prepare these videos, right? So certain books and certain websites to get the pictures have been used. So I would like to draw your attention to this slide here. We have already discussed this in conductometric titration, but at that time when I made that video, when I was moving this slide, this figure, this this line at the y-axis was originating from the origin, from the zero, which is not true. it should have a certain value of conductance initially. So it should start from, and that magnitude is smaller because it is a weak acetic acid and it is weakly ionized in the solution, right? So its conductance should be lower. So a y-axis value should be there, which I have shown, which I have corrected now, but it will not start from origin. It will start from the y-axis. It will have some intercept, but that will be of smaller magnitude because it's a weak acid, right? And then of course you can define all these by there is a slow increase first and then sharp increase due to addition of NaOH, right? So that's just a correction in the one of my previous videos. So with that, I thank you very much for your attention and stay safe. uh, if you have any questions, just let me know. Thank you so much. I will just end this lecture now.